Okay, so we're going to look at the second scenario where an object is dropped, so from rest, and falls down through a resisted medium. Now, this could be the second half of a journey if an object was actually thrown up. You could consider this as a separate case. So, falling down from rest. A particle falls from rest through a medium through which the resistance is proportional to the velocity and opposite in direction. So the resistance is proportional to the velocity. In other words, we're saying the resistance and opposite in direction. So we're talking about a force. Is it squared? No, the velocity is not squared. It's just minus mkv is that force. It's going opposite to the direction that we're talking. Now we're going to take gravity to be g. We'll just leave it at g for this question, because later on it talks about writing things in terms of g. So we want to find the velocity and the displacement, which I've written as y. That's normally, we've expressed it as x a lot of the time, as functions of t. Then we're going to find the terminal velocity. So there's going to come a point where the resistance that's pushing back upwards against it is equal to the force pushing downwards. So there's no acceleration at that point. So we're going to find the terminal velocity, and we're going to show that for a large height, the time to reach the ground is approximately that time there, if h is really big. So let's start by finding the velocity and the displacement as functions of time. So our first thing always with these questions is to write out a force equation. So I'm going to say that the overall force, my double dot, is the same as the force going downwards, mg, but we need to take off the opposing force, mkv. So we write our first statement out, which is a forces statement. Then I can divide by m. So I get y double dot is equal to g minus kv. And I'm going to want to be getting the velocity as a function of time. So this is dv dt is equal to g minus kv. dv dt equals g minus kv. I think I've got a little bit of room here to continue working that you'll be able to see. So I'm just going to say that dv on g minus kv is equal to dt. Now, the derivative of the denominator is actually minus k. So I need that on the top. So I'm going to just say minus 1 on k times minus k on g minus kv. So they're just sort of cancelling each other. dv is equal to dt. That way I can say that the derivative of this is sitting on top of it. So if I integrate this side and integrate this side, I can get minus 1 on k natural log of g minus kv equals t plus c. So I'll just bring that up here. Minus 1 on k natural log of g minus kv equals t plus c. And we can continue on from that spot. There. All right, I need to find the value of c. So at the start, it's moving from rest. So that means that t equals 0, v is equal to 0 as well. So when t equals 0, v equals 0. So minus 1 on k ln g minus 0 equals 0 plus c, which means I can see that c is equal to minus 1 on k natural log of g. So my equation is minus 1 on k, natural log of g minus kv equals t, and minus 1 on k, natural log of g. Now the question asked us to find both the velocity and the displacement as functions of time. So I need to make v, the velocity, the subject of this one here. So I might as well get the logs together would be a good idea. So let's bring that one over here. 1 on k, natural log of g, minus 1 on k, natural log of g minus kv equals t. So multiply by k and gather the logs together. We get that there. All right, so e to the kt is equal to g on g minus kv. And I'm going to need to move up to the top of the board. So g minus kv times e to the kt is equal to g. So g e to the kt minus kv e to the kt equals g. So minus kv e to the kt equals g minus g e to the kt. Am I still on the board? Yep. Okay. So get v by itself. V is equal to g minus g e to the kt on, and divide by minus k e to the kt. Okay, I'll just swap this around. So v is equal to g e to the kt minus g. Swap the top and get rid of that minus off the bottom. Now, that equation there, that's fine. But if I go to integrate that, I've got several parts with e's in them. That's my first issue that could happen. And I can see a way to make there only be one e sort of function cranking there. But also, it's harder to see what happens when time approaches infinity here, because we've got e to the kt on the top and the bottom. It's just harder to see, I'm saying. It would be easier if I divided everything by e to the kt, thereby getting only one function of e in there, and I'd be able to see what's going on a lot easier. So I'm going to divide everything by e to the kt. V equals g. So e to the kt divided by e to the kt is just 1, minus g on e to the kt on k, and that'll be just 1. So v equals g minus g e to the minus kt on k. Just go down a bit there. I like that better because there's only one e function there, which means it'll be easier to integrate. Of course, I could have divided here, like separated out the two terms and got a similar result happening. But I decided to do it that way. So we've got ourselves the velocity as a function of time. I was asked to find the velocity and the displacement as functions of time. So I'm just going to go ahead and integrate again. So I start at the top of my screen here with the velocity. Have you got that? No, velocity. Just there. All right, with the velocity is equal to g minus g e to the minus kt on k. So that's dy dt. Yeah, we commonly are writing dx dt, but I'm going all vertical. So dy dt is what velocity is in terms of time. And so I need to integrate that. Well, you know, this function here is just g on k minus g on k e to the minus kt. So if I integrate that, I'll go, that's g on k times t. And then this bit here will be e to the minus kt, and I'd have to do that, and that would give me minus g on k e to the minus kt. So there's my integral. Don't forget the plus c. There's my integral, but it's got the plus c on there. Now, I want to work out the plus c. Well, when t equals 0, y equals 0. Now, you might say, hang on a minute, it's way up in the air. It started from rest and it's dropping down. How can y be 0? But we said in the previous video that we choose our coordinate system such that the initial position of each stage of a journey is the 0 position. So that's 0, and as we go down that way, we're gaining values of the displacement. So, you know, if it was 100 meters down to the ground, it starts at 0, even though it's 100 meters high, and it ends up at 100. That's what we're saying here. So when t is 0, y is 0. Now, I just integrated that. So my notation's wrong here. I'm just going to fix up this notation. V is dy dt. Therefore, if I integrate both sides, y equals that. That's what I meant. Right? So when I put y is 0, if I put t is 0, I get g on k squared, because e to the 0 is 1. So c is minus g on k squared. So my equation that I want to use is y is equal to g on k t plus g on k squared e to the minus kt, and then minus g on k squared. So there's my equation for the displacement. All right, so I've answered the question about find the equation for the velocity in terms of time and the displacement in terms of time. Now they want to know what is the terminal velocity, and there's two ways to do that, right? Since they've just told me to find the velocity, that's g minus g e to the minus kt all over k. Since they just told me to find that in terms of time, I could use that, I could use that equation that I've found in part 1 to answer the question, what's the terminal velocity? As time goes on to infinity, right, what does the velocity end up being? So I can just set time to be very large and see what this value ends up being here. Well, what is the limiting value of this? As t approaches infinity, e to the minus anything approaches 0. So as t approaches infinity, this term is 0, and the velocity will be just g on k, won't it? All right? So as t approaches infinity, v approaches g on k. So the terminal velocity is g on k. But I'd like you to also understand what the terminal velocity is meaning. It's reached its maximum velocity, and it's not going to get any bigger, right? It's going to keep going at that speed, because it's at that point that the resistance upwards is exactly equal to the gravity force pulling downwards. So there's no net force acting upon the particle as it falls. So it maintains the same velocity because of that's Newton's first law. It continues in a state of uniform motion in a straight line and less acted upon by net force. So it'll continue with that constant velocity, that terminal velocity. importantly, what I just said is that the force of the resistance and the force of gravity are equal. So if we put them equal, we will be able to work out the answer without having to find the equation of the velocity in terms of time and sending time to infinity. So right back at the beginning, so if I want to find the terminal velocity without doing all this, right back at the beginning, I had said that y double dot, the acceleration, is g minus kv. But I'm saying at terminal velocity time, there's no net force. That's all balanced, which means that there's no acceleration on the system, on the particle. So 0 equals g minus kv. So kv equals g. So v equals g on k, which is what we found from that equation there. So if you were just straight asked to find the terminal velocity, of course, you could just do that. But the question did say they wanted to know the velocity as a function of time, and they wanted to know the displacement as a function of time. And then, after finding the terminal velocity, the question wanted me to show that for a large height, the time to reach the ground is given by a particular equation. So I'm just going to come back over here because I'm going to need this equation for height. And I'm going to give myself a bit of room to work to answer that last part. So here's my equation for the height, remembering that up there it's 0 at the start and it falls down to something massive, right? Maybe it's hundreds of meters down, right? If the height is large, then of course the time is large, right? So if height is large, then time is large. That's an important factor. I'm basically sending time to infinity in this equation. So this equation is y equals g on kt plus g on k squared e to the minus kt minus g on k squared. So that's that. Now, that means t is really big in this situation. Now, let's let t get really big. Then what's going to happen here? That's going to go to 0, isn't it? So if h is large, t is really large, and this approaches 0 if h is large because t is large. So y will be h, and that'll be g on kt minus g on k squared, since g on k squared e to the minus kt approaches 0 when t is large. And t is large if h is large. Which means if we rearrange this for t, h plus g on k squared equals g on kt. So kh plus g on k equals gt divided by g, kh on g plus 1 on k equals t. And they were wanting us to show that it was kh on g plus 1 on k. So if it's large, then h is approximately equal to this, because I did take out this term which isn't quite 0. So the time is approximately kh on g plus 1 on k.